Hello, welcome to our first seminar of 2021, and today I'll be talking about programming GPUs with Fortran. This is aimed at people who use Fortran in their daily programming, but who have not used GPUs. So I will introduce very briefly what GPUs are, what is the basic idea about computing with GPUs, and then I will show you some Fortran code. So one slide of very quick introduction. So GPU stands for Graphics Processing Unit. If you play games on your desktop, you probably have this kind of a device inside your desktop. And these things are still primarily, the performance is primarily driven by computer gaming market. But in the mid-2000s, GPU makers realized that these can also be manufactured and sold as general purpose computing devices. And they have been adding functionality gradually to make them better at this. In particular, since 2007, we even have server quality GPUs, which are not used for graphics at all. They sit inside servers and clusters, and they just crunch numbers. And recently, it has been found that GPUs are excellent at deep learning AI workloads, and they have become even more popular since. So just to give you an idea of how useful it might be to port your code to the GPU, here is a list, a partial list of the GPUs we have at Compute Canada. So our major clusters like Graham, Cedar, and Beluga have hundreds of GPUs on them. So whereas in previous years, GPUs were somewhat exotic and it might have been difficult to find a meaningful amount of GPU hardware to use, now it's becoming more popular. And this is why it's important to be aware, if you are a programmer in Fortran, what possibilities there exist to maybe port your code to the GPU. So CUDA is the default NDK released by NVIDIA. So NVIDIA is the primary manufacturer of high-performance GPUs, at least HPC quality GPUs. They have somewhat of a monopoly on this. And the standard programming tool that one uses to program those GPUs is CUDA, which has been around since 2006. So CUDA is conveniently free to use, but it is based on the C language. So Fortran programmers, unfortunately, have a problem with CUDA. So to mitigate this somewhat, in 2010, a company called PGI, the Portland Group, a company which makes compilers, released CUDA Fortran, which is a way to program GPUs in Fortran, basically porting CUDA to Fortran. And as far as I know, this is still the only way to program GPUs in Fortran. And initially, so this was released as a commercial product. So you had to buy the PGI compiler license to use this. Now, PGI was in turn acquired by NVIDIA in 2013. And since then, PGI compilers have been made freely available to the scientific community. And in fact, recently in 2020, NVIDIA has finally folded the PGI compilers into what is called the NVIDIA HPC SDK, Software Development Kit. I mean, this is mostly just changing of name. The functionality is still mostly there. So today, everything that I will show you is done using the CUDA Fortran compiler released by PGI/NVIDIA. So what is the difference between GPUs and CPUs? Let me just give you a quick cartoonish view of what it is so that you have some understanding of the pluses and minuses of using both. So both a CPU and the GPU, they both have a computer chip in it, manufactured using similar techniques. And the only difference is basically the decision of how one constructs this chip, how much real estate does one devote to certain functions. So here one can see that a CPU is meant to be a kind of a jack of all trades machines. So it will have a certain number of cores to do calculations. So your desktop will have 4 cores, 8 cores. A cluster machine will have way more, 40, but it's a relatively small number. And each one of these cores is quite powerful. It can do some vector instructions, single instruction, multiple data. But quite a lot of the chip also has to be devoted to control circuits because each one of these cores is meant to run different things completely independently of each other. And you also need to have a cache to ensure quick access to memory. So in comparison, a GPU is different because it allocates much more of its resources to just pure computation. So you have many more much smaller cores, and they occupy most of the area. But the trade-off is that you don't have the cache. That's one trade-off. And then the control, you have a little bit of cache, but not much. And the control area is also much smaller. What this effectively means is that these cores on the GPU are not independent. In fact, to really work together, they have to be doing the same thing. So this is just a very brief view, but essentially the GPU can do more calculations, but with some constraints. That's the message to take away from this slide. So a GPU is an accelerator. It is not an independent computer. It is something you add to your computer to make it run faster. So when you use an accelerator, you have the basic question is how much speed up do you get? So if you add the GPU to your computer, how much faster will your program run? What are the possible values? Well, the range is quite vast. So at one extreme, you might get no speed up at all, because as I've shown in this picture, the GPU has a very specific architecture. So your code has to be able to fit this architecture to have any kind of a speed up. In particular, you can see that the GPU has a very large number of cores. We are talking 4,000 cores on modern GPUs. So any parallel program you want to run on this has to use at least 4,000 threads and really many more to actually take advantage of this, to use all those cores. So if you cannot split your program into that many threads, you will not get any kind of a speed up. In fact, your code will run slower. So this is one extreme. The other extreme is really highly unusual, but essentially if your serial code is particularly bad, running on the CPU, doesn't parallelize, but it parallelizes well on the GPU, then you will get a huge speed up. But those are untypical results. Though I will actually show you at the end of this lecture a code where there is actually that kind of a speed up. So these are the extreme values. But if your code parallelizes relatively well and you do a relatively good job, then you can expect something like a 10-fold to 80-fold speed up over a serial CPU code. So if you have a code which has not been parallelized at all, it just runs on the CPU. If you parallelize it to run on the GPU, it will be between 10 and 80 times faster, and 30 times is considered worthwhile. So this is one possible comparison. However, if we take a code which is already parallelized on the CPU, so it uses multiple cores, then in this case, at best, we can expect a 5 to 10-fold speed up. So if you compare a multi-core computer using all the cores versus a GPU. Now, these are very, very approximate numbers because every computer setup is different. And this speed up, if you are doing your own coding, this speed up will depend a lot on the problem structure, so how easy it is to parallelize, and also how good you are coding CUDA. Unfortunately, coding CUDA well requires some insight into hardware. You cannot just have the compiler do all the work for you. In fact, the human has to do all the work pretty much. And that's why speed up requires a lot of programming time in a way. So that's something to consider as well. But let me make this more concrete. So let's focus on a piece of hardware which I actually use to do all my timings and what I will show you in the rest of this seminar. So Beluga is our newest GPU cluster, our newest cluster of GPU nodes, and it was turned on last year. It's about a year old at this point. So it has so its nodes have an Intel Xeon Skylake CPU with 40 cores, which runs at 2.4 gigahertz. Now, each one of these cores is capable of performing 64 vectorized single precision floating point operations per cycle. And by the way, if you prefer to use double precision, just divide everything by 2. So 64 vectorized single means 32 vectorized double. But anyway, so a single core can do 64 vectorized single precision. So the whole CPU can do 40 times 64, which is 2,500 single precision floating point operations. And this chip runs at 2.4 gigahertz. So this lets us know how many operations it can do per second. If we compare it to the NVIDIA Tesla GPU, each node has 4 GPUs in it. Each one of these runs at 1.2 gigahertz. It has 80 multiprocessors, each with single precision CUDA cores. So the total number of operations it can do, the whole node is 4 GPUs, that's where the factor of 4 comes from, times 80 multiprocessors on each GPU, times 64 single precision CUDA cores inside each multiprocessor, which is 20,000. But this runs at half the clock of the CPU. So overall, we can conclude from this that just in terms of theoretical maximum, how many floating operations you can do, 1 Volta GPU is equivalent to the entire 40-core CPU. But because there's 4 GPUs inside the node, it's actually 80% of the computational power of the node comes from the GPUs in this case. Now, of course, these are just theoretical maximums. Any actual performance will fall short of this. For example, this doesn't count the amount of time it takes to access memory. This clearly will slow things down, but it does give one a basic idea of what kind of performance you can expect. And the takeaway message is that these days, Intel has been working very hard to make their CPUs competitive with NVIDIA GPUs. And at this point, at least in this example, the GPU is equivalent to a very fat 40-core CPU. So a GPU is a coprocessor. So in terms of how you actually write CUDA code, here's a simple diagram which demonstrates the idea. So the GPU, you cannot log into a GPU. A GPU is on a device. A GPU is just something you add to the CPU. So any code you are running on the CPU essentially starts on the CPU first. So the CPU initializes the data. It acquires the GPU. It can do its own computation. Now, at some point, it arrives at a function which can be offloaded to the GPU. So at this point, the host code, the CPU code, copies over the data that is to be processed, and it starts a function which we call a kernel. And so device in this case is the GPU, and the kernel is a multi-threaded function which runs on the device, on the GPU. So here, all these arrows demonstrate the massively multi-threaded nature of this kernel function. Now, this execution is asynchronous, so while the GPU is computing, the CPU can actually proceed to do something else, which is demonstrated by this arrow. So asynchronicity is possible. And then once the GPU finishes its multi-threaded computation, it can synchronize with the CPU. The data can be loaded back to the GPU, to the CPU. I mean, it can be loaded from the GPU to the CPU, and that the CPU can either do this again or exit. The red arrows here, by the way, these data transfers, they are not trivial data transfers. As we will see, the interconnect between the GPU and the CPU is relatively slow. So there's a cost to just offloading a function to the GPU. So you might have a function, and again, we will see this shortly, you might have a function which will run faster on the GPU, but the amount of time it takes to transfer the data means that it's not worthwhile to offload it to the GPU. It just takes too long to copy the data. In other words, to use the GPU, you must have a program which spends a relatively long time computing on the GPU in comparison to the amount of time it spends moving the data. So to illustrate all this and to finally see some code, let me start with a very simple example which is used very commonly in this kind of training, and this is SAXPY. So this is scalar alpha x plus y. It's a very common linear algebra operation. So it's just an addition of 2 vectors with 1 vector multiplied by a scalar. So alpha is a scalar. We multiply each element of vector x by that scalar. Then we add vector y. This is an element-wise addition, and this results in a new vector y. So how would one do this in default Fortran, just vanilla Fortran? Well, here is a subroutine which does this. So it's a subroutine which takes x, y, and a as arguments, and it does a loop from I equals to 1 to n. It does a loop over all the elements of y and x, and it just applies the operation. So it's relatively simple. So this is what this would look like in CUDA Fortran. And I will walk you step by step to explain the differences between these two subroutines. So first, there's a rather obvious difference. We have an attribute global in front of our subroutine. This is what tells the compiler that this is meant to run on the GPU. So this is the first difference. The second difference which jumps out is that we no longer have a loop. Instead, we have these block IDX, block dim, and thread IDX. These are built-in variables which identify a thread. So what the GPU does when you call a kernel, so when you call this function will, many threads will be created, and different threads will run different instances of this function, except that different threads will process different element of the vector. So the thread has to identify itself. And in CUDA, the convention is that we don't just use a single number to identify a thread, but CUDA insists that you use that threads are divided into blocks. This has to do with the way hardware actually runs these threads. Each block ends up running on a single multiprocessor. So a thread, at minimum, has to have two IDs. It has to have an ID number saying which block it is in, and the ID number within that block. And there's also block dim. This indicates how many threads there are in the block. So what happens is when we launch, and these are built-in variables, so they just come from CUDA itself. So when we call the function in our host code, so we call SAXPY, we assign, in addition to the function arguments we give, we also have these extra arguments in these triple brackets, where the first argument is grid, and this indicates how many blocks there are. And then the second argument is block, which indicates how many threads there are in each block belonging to the grid. So to illustrate how this can be used to find the location in the array that each thread is responsible for computing, let me use this picture. So imagine that we launch a kernel and we launch many threads, and let's see what happens in a particular thread. So a particular thread starts running its code. So this thread, using these built-in variables, can identify which block it is in, how many threads there are in a block, and then which thread it is within the block. So in this example, I have a thread which wakes up, it gets created, and it knows that it's in block 4. Each block has 8 threads, and it is thread 6 inside its block. So to compute the offset, using this formula here, this becomes 4 minus 1 times 8 plus 6. So if we actually count it, this thread knows it has to process element 30. And by the way, for me as a C programmer who programs in C, I had to constantly remind myself that Fortran counts all the elements from 1, not from 0. And similarly, threads are indexed not from 0, but from 1. This is why here we need to have block idx dot x %x minus 1 to account for that. So so this is, if this is perfectly obvious to you, that's great. If you need a little time to think about how this works, please do, because it's a kind of a fundamental idea of CUDA programming. So let me now put the CPU and the GPU code side by side to again reinforce what's happening. So in our kernel code, in our CPU code, we have a loop. This is now replaced by a code which, so instead of a loop, we have a code which is called in a large number of threads, where each thread processes what would have been one element of a loop. So each thread figures out which I it's responsible for handling, and then it handles just this particular iteration of it handles the operation which would have corresponded to one particular iteration of the loop. And finally, how come we need to have an if statement here? This is because when we launch our kernel, it's quite possible that we will have more threads than we have elements inside our vector. So we need to make sure that I doesn't read out of bounds, and this is why we need to have this if statement. We could avoid it if we could guarantee that we always launch exactly as many threads as there's elements in the vector, which might be doable, but if our vector, for example, has a prime number of elements, then there's actually it becomes impossible to launch our kernel in where we have a product of 2 elements, especially because there's actually a restriction on how big blocks can be. So a block can be at most 1024 threads in a single block. So this is just the kernel subroutine. So this is the subroutine which runs the operation itself. And of course, we need the full code, the host code, which launches this subroutine. So let me now discuss what this host code looks like. First, let me just describe in words what it has to do. So the host code has to initialize the device somehow, initialize the input arrays in host memory, upload the data to the device, execute the kernel, download the results, and then check the results in our case. Now, the nice thing about CUDA Fortran is that it actually can make a very compact code. It's in many ways more convenient to use than the C code. So in my summer school course, the host code would take 3 or 4 slides, but here everything fits on one slide. So let me explain what's happening. So here's my main program. I have to have this line to enable CUDA Fortran. And by the way, you can see that everything here looks mostly like conventional Fortran with some additions. So that's how CUDA is in general. It's just a conventional programming language with some additions. Now, here I define the variables to hold the values x and y on the host. And I also need arrays to hold this on the GPU. So the GPU has its own memory. It will not use the host memory. It has to upload the data to its own memory. So I declare now 2 device arrays, and the device keyword here indicates that this will live on the GPU. And I call my arrays x_d and y_d. The underscore d here is just to indicate to me that this is a device array, but I could have called it anything I wanted. And I also need a special structure to hold the information about the grid and the block structure of my kernel. So this structure, as the name implies, can be 3-dimensional. So your block structure can be 1, 2, or 3-dimensional. In this case, I have a 1-dimensional vector, so it makes perfect sense just to have a 1-dimensional decomposition. So here I choose my block size to be 256. As I said, there's a limit to how big this can be. 1024 is the maximum set by the hardware. And it's a good idea to make it a nice power of 2 for reasons which I will not go into. And then to make sure that I have enough threads to process all of the n elements inside my vector, I take number of elements divided by block size, and I just bump it up using the ceiling function to make sure that I basically have always have more than enough threads to handle all of them. Okay, so here I initialize my variables on the host, and I just set all of x equal to 1 and all of y equal to 2. Fortran allows me to do this with it's just a simple statement like this. And now I need to copy my data from the host to the GPU. And in Fortran, CUDA Fortran, this is very easy. It actually figures out, the compiler figures out what I need to do just from this simple statement. By the fact of copying from x to d, by the virtue of the fact that this is a device array, this will accomplish the copying from the host to the device. Now, this might look deceptively simple, but as we will see, this step can take a significant amount of time because what is happening is that data is being sent from the CPU to the GPU. Once the data has been copied, I call SAXPY using the grid and the block structure I defined before. Once SAXPY is done, I then copy the data from the GPU back to the CPU. So the important thing here, I want to check the data on the host in this example. So I just do the copying where I populate the variable y on the host with data from y on the device. Let me say a little bit of synchronization here. So as I said before, GPU and the CPU are asynchronous. So when I call this on the host, the CPU just keeps on going. It doesn't stop here. But where synchronization will happen is at this step. So whenever I copy memory from the GPU to the CPU, it can basically be assumed that the CPU code will stop in this line until the copying has been completely finished, and the copying will not start on the GPU side until the kernel has finished the calculations. So there's no worry about copying too early before the GPU finishes the calculation. But in more advanced codes, synchronization between the GPU and the CPU is something that you do need to worry about. Okay, so the main elephant in the room for this code and why a simple code like this would actually not even be faster when you add the GPU into the mix is the slowness of the data transfer between the GPU and the CPU. So in this example, this is the data actually collected on a different cluster on Graham, but the Beluga is similar. You can see that on the CPU, I have 128 gigabytes of RAM, and the bandwidth between the CPU and the GPU is 100 gigabytes per second. And similarly, the GPU has its own 12 gigabytes of memory. Again, this is on Graham. It can do 5.3 teraflops of calculations, and has a greater bandwidth, which sort of makes sense because it can do so much number crunching. It needs high bandwidth to memory to actually supply the computational circuits with data to operate on. So this is 380 gigabytes per second. But the data between the CPU and the GPU has to go over a PCI bus, which is a kind of an old-fashioned, still very common, but nevertheless rather slow interface. And in this case, I measured the bandwidth to be only 12 gigabytes per second. So what this implies is for the GPU usage to be worthwhile, you have to move your data over and you have to keep it on the GPU. You have to do a significant amount of computation so that the amount of time it takes to copy the data is insignificant compared to the amount of time you're spending computing on the GPU, which is not the case in our simple example. So if I want to run this example on our systems, you can run it interactively. So on our major clusters, there's the salloc command, which allows you to grab some node for interactive work. This is meant for quick, short runs for testing, which is exactly what we are doing here. So if I called salloc, specify the time, 1 hour in this case, specify that I'm requesting a GPU, and then your account name, this will give you an interactive node. It might not happen right away. Obviously, a node has to be free, but we do have a certain number of nodes kept in reserve, not busy precisely for this kind of work. So it should start reasonably fast. And once you get your program working, you want to probably run it as a job. So you can submit a job to the GPU queue with it's the way you would usually submit one, except you request GPUs as well. And if you want more information about this, we have a special page in our help wiki devoted to this. So in the tests I did, I ran salloc. This gave me a GPU. Actually, I didn't ask just for a single GPU in my case. I also asked for CPU resources when I was testing the CPU case. So this is a busy slide, but I wanted to put everything in one place to be able to compare results. So first, I ran the GPU version. So to do this, I load our standard environment 2020, and I load the NVHPC module. So this is the module which contains the CUDA Fortran compiler, which I'm using, and I also load CUDA. So to compile my code, I put all the code I've shown you goes into an extension, file of extension.cuf, and I compile it with NV Fortran, which is the name for the NVIDIA Fortran compiler as provided in this new development kit. So I compile. Notice that I don't provide any additional option because I don't need to. The compiler, there's usually not that many options you need to provide when you're compiling for the GPU. And then I use a profiler conveniently provided by NVIDIA, which is called NVProf. So you can run NVProf on any CUDA executable and get nice profiling information. And this tells me that here is my kernel. So this took 1.94 milliseconds to run. But unfortunately, you can also see that most of the time, 99% of the time was spent by the code in CUDA memcopy. So when I was copying my host arrays to device arrays and then the other way, device arrays to host array, what CUDA Fortran is actually doing, it's calling a CUDA memcopy routine. And because this goes over the relatively slow PCI bus, it really takes much, much longer than actually running the kernel. So in comparison, when if I want to run the CPU code, so I put my code in a conventional F90 file. Now in this case, I load our PGI module, compile with PGF95 with a fast option to make sure it's optimized. With the minfo option, I want to see whether it vectorizes correctly, and targeting Skylake architecture, which is what we use for Beluga. And the compiler reports that yes, vectorization has been performed. So we are comparing vectorized code to the GPU. So I now run a pgprof, which is similar to nvprof, similar idea. You run this on our executable. And this tells me that the kernel here took 79 milliseconds to run. So you can see that the GPU, just for the kernel itself, the GPU is about 40 times faster than a single core but vectorized CPU code. So there is speed up. However, because of the amount of time it takes to copy the data, we don't get overall speed up when we run this on the GPU. But of course, the moral of the story is that in a real-life calculation, you would probably not do a single SAXPY operation or a single matrix multiplication or whatever, but you would do many for each copy. So if you did this, then this speed up, the fact that the kernel runs 40 times faster would be of increasing benefit to you the more time you spend on the GPU. Okay, so to again reinforce this idea of CUDA programming in Fortran is like, I will now show you an exercise which we do in our summer school, but I ported it to Fortran. So the standard exercise we do has to do with computing the Julia function. So we give students a starting CPU code, which is already there, and they have to convert it to a GPU code. So a few words about the Julia set. So if you take a point in the complex plane, a point Z, and you apply the following transformation to it, you square it, so you square the number, you add some constant, and then you repeat, and you keep on doing this. The result of the sequence you're getting will either converge or diverge. So it either goes off to infinity or it remains finite. So the Julia set is defined as the set of points in the complex plane for which this iteration remains finite. And the points outside the Julia set are those for which this diverges. And of course, the interesting idea about Julia sets is that the set which you get is highly non-trivial. Even though this iteration is so simple, you get this nice complex fractal pattern. So in the code which I will run, I need to have a function which evaluates whether a particular point in the complex plane is in the set or it isn't. So I will call this function Julia. And then to make a picture, I essentially have to compute an array of pixels. So I have a two-dimensional array of points in the XY plane, where I map each point in the XY plane to a particular complex value. And then I evaluate the Julia, a function called Julia on each point to see whether I get a 0 or a 1. If I get a 1, that means that the point is in the set and 0 otherwise. So you can see that a very natural GPU parallelization can present itself here because each calculation for each pixel, so to speak, is independent of the other calculations. So I can have one thread per pixel, so to speak. And if I have 2,000 by 2,000 pixels, so that's 4 million. So that's a large number of threads I can run. So 4 billion threads is quite something quite easy for CUDA to cope with. It's meant to run with a large number of threads. So first, let me show you the CPU code. So this is something that the students would start with. So here's the Julia function. It takes two arguments x, y, which are essentially two-dimensional coordinates. And then it applies some kind of a scaling to get the z value with some real and imaginary part. And now it does the iteration. So it iterates over this function. And here we do it 200 times. And our criterion for divergence is if the absolute value of these z exceed 1,000, then we consider it to have diverged. And then we have a 0. And otherwise it returns a 1. The important thing to note here is that the iterations of this loop are not independent. Each iteration depends on the previous iteration. So this is not so we don't want to decompose this loop into multiple threads because it will not work. We don't have independent threads. So essentially, when we convert our code to the GPU, we will not touch this function. We will not parallelize it. We will have one thread on the GPU run each instance of this function. And then we have a subroutine called kernel, which even though this is running on the CPU, I've chosen the name kernel because this will have to be turned into a kernel on the GPU. And here we have a double loop because we are iterating over a two-dimensional plane. It makes sense to have a double loop. And we call our Julia function for each value of x and y set in this loop. And this will return an array, one-dimensional array we call where we store the zeros and ones depending on what the value was. And finally, the host code is very simple. We call the kernel function. It actually doesn't have it doesn't have to read anything. R is just the output here. And then we write the data to the output. So to convert to the GPU, essentially, we will have to get rid of these two loops and instead change this to a CUDA kernel. And we'll have to also copy the data out of this kernel once we call it because the GPU doesn't have access to our disk. So to write out any data, we have to copy it over to the host and write it out there. Okay, so in general, when you're converting a CPU code to GPU code, you're looking for loops with independent iterations. So again, to reiterate, calculating f of z, that's not an independent loop, so you don't want to touch this, but you want to parallelize the loop over the pixels. So let's now talk about each. So this is now the GPU code. Let me describe the changes which I need to make. So for the Julia function, I don't change it at all, but I do have to say that this is a function which now will be running on the GPU. So the compiler requires me to now specify that this is a device function, this is a GPU function. Even though the syntax of this function doesn't change otherwise, it still has to be declared as a GPU function to the compiler. So the major changes in the kernel function, where now instead of loops, I use threads. And because I had two nested loops over x and y, in this case, it makes perfect sense to decompose my threads into a two-dimensional arrangement. So instead of blockdim x, I have blockdim x and blockdim y. Instead of thread ID x, I have x and y. Essentially, this means that instead of being identified with a one-dimensional coordinate, each thread is identified with a two-dimensional coordinate. This is something in CUDA which is supplied for the convenience of the human programmer, essentially. When you have a problem which is intrinsically two-dimensional, it's much easier for the human programmer to think in 2D than in 1D. And in this case, we had a loop over x and y. I mean, we had two nested loops, one over x, one over y. So it is really convenient to just use a two-dimensional decomposition because you have this one-to-one mapping. And finally, this is the main host code. So actually, in this test example, I have been running the loop over multiple times just to make sure that I get a long enough run to get sufficient timing. So that's actually a pretty good idea whenever you're timing something on the GPU. If your kernel takes a really short time to run, you might get some spurious results. So it might be a good idea to run it multiple times and take the average. So I tried various values in what I was doing during my timings. But the final numbers I will show you is for just one iteration to be consistent. So here I will now want to run my calculation on the GPU. So in addition to my ARR array on the host, I need to declare device array of the same size, which will live on the GPU. And I also have to declare the grid and block structures to hold the information about the blocks for the threads. So as I said, now I use a two-dimensional thread decomposition, and I decide to make my block 32 by 32 threads, which is 1024, which is the maximum block size I am allowed to have. So no matter how many dimensions I use, the maximum number of threads per block is 1024, and it is a hard limit. Your code will give wrong results if that's not the case. And then I want to make sure that I have enough blocks in my grid. So again, I use the same approach as before. I take my dimension. Notice that 2000 is not evenly divisible by 32. So I have to take 2032 plus 1 essentially to make sure that I have enough threads to cover all of the pixels. And then once I have my thread structure, I call my kernel using the grid and the block values I defined here. And once I'm done, I copy the data back from the dev, from the device to the host. And here, just to save space, I cut out the part when I write the results to disk, but that would also, this would be identical as it was in the CPU code, just to write out the results to disk. Okay, so finally, let's take a look at the results here, the timing results, which are quite instructive. So, so to run the GPU code, I used first loaded the usual modules, so standard environment 2020, NVIDIA development kit, CUDA 11, compile my code in a .cuf file with NV Fortran, and then I run the code while profiling. And here I can see that, again, the code is dominated by a data transfer. So 96%, 97% of the time is spent copying the data over. after the calculation is done, but the kernel takes only 200 microseconds or 0.2 milliseconds to run. And let me compare to how this code does on the CPU. So again, as before, I load the PGI module. I compile my code with, make sure it's optimized, get the information about vectorization, target Skylake. But here the output is important. Notice that it tells me that vectorization has not happened. So loop is not vectorized, potential early exit. So remember that in my function, I have return statements in my Julia function if the operation diverges. And I also have a call to the Julia function. And at least in this case, the compiler doesn't like this and it doesn't believe it can safely vectorize this. And the result of lack of vectorization means that the CPU code is vastly slower than the CUDA code. In fact, it's ridiculously slower. I mean, look at this. The CUDA kernel here took 0.2 milliseconds, and here it took 319 milliseconds. So that's a difference, the factor of 1500. But again, if you think about it, based on the numbers I've shown you before, it makes perfect sense. It is essential that to have any hope of competing with the GPU in any way, the code on the CPU has to be vectorized. If you're not vectorizing it, then you will get terrible results. So this is a nice, somewhat pathological example, admittedly, of what happens here. My CPU code has been quite simple. I could have taken more care to write my CPU code to ensure that vectorization does occur. But in this example, though, it's interesting to note that in a sense, CUDA is much better at vectorization. The complexity of the CUDA code is similar to the complexity of the pure Fortran code, and nevertheless, CUDA was able to vectorize it, i.e. distribute it between multiple CUDA cores without any extra effort, whereas on the CPU, it seems that extra effort would have been required to make that happen. So this is the end of my talk. We didn't have too much time, and this is just barely scratches the surface of how to use GPUs. We have just seen some very simple codes. Of course, GPUs can do more complicated calculations with more complicated dependencies between threads. We have a 2-day CUDA course in our summer school, which is coming up in May or June. So you can definitely feel free to come to this. Just based on the demand, it will be taught in C because unfortunately, the community of people using Fortran to program GPUs is relatively small. But if you are a Fortran programmer, I hope you can take away from this seminar the idea that programming GPUs in Fortran is quite possible, and NVIDIA seems to be fully behind this by putting in CUDA Fortran in their default high-performance computing SDK. Thank you.